Special right triangles. So while trigonometry, sine, cosine, and tangent can be used on these special right triangles, we can also come up with much more specific answers. All of these two triangles are going to be including square roots. So instead of having a decimal equivalence, we can write it as a square root. Now the very first type of triangle is a 45, 45, 90 degree triangle. So on a 45, 45, 90 degree triangle, first of all, notice it's isosceles because these two sides are going to be the same because the two base angles are the same. And then obviously the hypotenuse is slightly different. Now, in a 45, 45, 90 degree triangle, the sides are x, x, and x root 2. Now, when you refer to the sides, you always consider it as the side across from an angle. So across from a 45s are both x's. Whatever that number happens to be. This is kind of like the special number you're looking for. And across from the 90 is an x root 2. So you're going to be using these charts that looks just like this, and your goal is to find x. And x is kind of like the dilation maybe that you're looking for. It is like the special number for that triangle. So let's just say that x equaled 1 in a triangle. So it's the original 45, 45, 90. If x was 1, then the side lengths would be 1, 1, and 1 root 2. Now if I made it twice as large and x was 2, so that's kind of where I think of it as like a dilation number, wherever there's an x, I'm going to put a 2. So the side lengths would be 2, 2, and 2 root 2. And I could keep going. If x was 3, I'd have a 3, 3, and 3 root 2. So you can find all of the side lengths by figuring out what is that main number for that triangle. What is the x? So let's try one of them. So let's just say we had this triangle and this side was a 3. So I want you to create these tables because it's going to help you collect your information and your work as you go. So the side length we know is across from a 45. So in my table across from a 45, I'm going to put a 3. Well, what this is telling me is that the number I'm looking for, my x value, is a 3. So that means that my other side lengths are also a 3, and then across from the 90 is 3 square root of 2. Now again, we could figure out the decimal equivalent of 3 times the square root of 2, but we're not going to. We're going to leave it as a square root. It keeps it as a nice contained answer. So if I wanted to, I could label this as this side is 3, and this side is 3 root 2. So on this problem, the special number we're looking for was a 3. Okay, let's try this one. So on this one, across from the 90 is a 10 root 2. So in my table, I'm going to write a 10 root 2. Now what's nice about this answer is the root 2's match up, so those are like the same. And what I notice is that the number I'm looking for, my special x, is a 10. So that means that these two sides are both x, they both have to be a 10. So these are both side lengths of 10. So it's like my dilation was of a 10. Okay, so my root 2's matched. Everything else, x was 10. Okay, the second type of special right triangle is a 30, 60, 90 triangle. So on this one, across from the 30 is x. So across from the 30 is the number we're looking for, is that special x. Across from the 60 is x times the square root of 3, x root 3. And across from the 90 is 2x. So when you figure out that you have a 30, 60, 90 triangle, the table of values that you're going to come up with is this. Now again, let's just say that we figure out that our special number of x is a 1. So it's kind of like it's our original dilation. Then across from the 30 would be a distance of 1, across from the 60 would be 1 root 3, and across from the 90 would be 2 times 1, which is 2. If I found out x was 2 in a triangle, then across from 30 would be 2, across from 60 would be 2 root 3, and across from 90 would be 2 times 2 is 4. Or if I found out it was 3, across from the 30 would be a 3, across from the 60 would be a 3 root 3, and across from the 90 would be a 2 times 3, which is 6. So we're trying to, again, figure out what is our x value for a specific 30, 60, 90 triangle. So let's try one. So here is our triangle, And across from the 90 degree, the 60 degree is a 5 root 3. So in my table, I'm going to put in the 60 area, I'm going to put a 5 root 3. So our root 3's match, that's good, which means that my x value that I'm looking for is a 5. So everywhere I have an x, I'm going to put a 5. So across from the 30 is just 5, and across from the 90 is 2 times 5, which gets me a length of 10. So this is a 5, and this is a 10. Okay, last one. I didn't want that. Yes, I did want that one to be 5. Okay, so let's just say we had this triangle here, 30, 60, 90. Now across from this 60 is a 5. Now on this particular triangle, I don't have a root 3 with my 60. So sometimes you're going to have to do a little bit more solving to figure out what your special x value is. Now, one of the ways that you can figure this out, or the main way, is this is actually an equation that we can solve. Because somehow our x value was multiplied by the square root of 3 and we got an answer of 5. Well, that means x root 3 somehow equals 5. This becomes an equation with just an equal sign in between. And what I can do is I can solve it for x. So if x is being multiplied by the square root of 3, I'm going to divide by the square root of 3. And x now equals 5 over the square root of 3. Eventually, probably in Algebra 2 or Geometry, you'll learn about rationalizing the denominator, but we will not be doing that today. That means not having a square root in the denominator. So our special number for this one's a little bit more interesting looking, but it is just 5 over root 3, which means across from the 30 is x, which is 5 over root 3. And across from the 90 is 2 times 5 over the square root of 3. I'm going to make that as a 2 over 1. So 2 times 5 is 10 over the square root of 3. So if it's not an easy thing to notice, especially if there's a square root involved, you're going to solve this equation to find x. And that's why that chart is very helpful to have.